All right, copying DNA. So this is DNA replication. And we call this process semi-conservative because if this is the original strand in the blue, we use the original strand to make copies. And each side of the original strand is used as a template for a new strand. So any new DNA, we say, has half of the parent template and half of the new DNA. So it's half and half, okay? And here you see the end result, and the light blue is showing the new DNA strand, and the darker blue is the old DNA strand. So here's that word I use, semi-conservative. Be able to talk like a scientist, okay? So you need to know this word. The strand of a double helix separate and act as a template for the new strands, making the process semi-conservative. That's the wording and the way that you need to understand when we say DNA replication is semi-conservative, okay? In layman's terms, you take one of the old and it's used as a blueprint for the new. So each new strand has one old, one new. To use it in science words, you would describe it as the strands of the double helix separate and act as a template for new strands, making the process semi-conservative, okay? DNA replication, one thing you're gonna see with DNA replication is think about how long one chromosome is. They're ridiculously long. So DNA replication doesn't start at the beginning of a chromosome and go all the way through. It actually happens in several areas of one chromosome. So here you see this little bubble. DNA replication, we call this bubble basically the replication bubble, and you'll see it's happening several places within a DNA strand, okay? And large groups of enzymes come together and make this happen. Where the replication begins, we call is the origin of replication, and there's gonna be several of these sites along one strand of DNA. Okay, so here's a quick summary. Excuse me. We went over this briefly last year. You had to know the idea that it was semi-conservative. You had to know that part of the new and part of the old. Now, the one thing I don't go into a lot of detail in general bio, and you did need to know some of these enzymes, is this idea that we're going to talk about. You have, when this occurs, you have two different things happening, okay? If you start one of these strands, we call the leading strand, and life is easy. It literally starts at the beginning of the DNA strand, that's right here, and it just zips on through. And as the DNA opens up, more nucleotide bases are added, okay? But now we have this guy. He makes things difficult. This is the lagging strand. The difficulty with the lagging strand is that this original enzyme, and I would really encourage you, there's a bunch of videos embedded throughout this PowerPoint. I'm not gonna put them all on the Google Classroom as links. I'm just gonna say, open up your Google slide presentation and go ahead and hit on every one of these links. This is a process that you need to see in order to understand. So I can try to explain it in pictures, but a lot of these videos are extremely helpful. But I don't want to take time within my video to play these videos. So please, if you see a link, hit it and watch it. So this guy, the first enzyme is helicase, right here, these two little proteins. And basically that, well, there's more than that, but these two purple guys right here that are shown in this video, or this picture. And it basically unzips the DNA string and keeps it. Then we have these single strand binding proteins. These guys keep it unwound once it's unzipped. If you've ever tried to pull something apart that's sticky, it keeps sticking back together. DNA is like that. So we have these little single strand binding proteins that keep it separated, and they're very helpful. And that's gonna be new this year. You didn't know about those last year. Now, here's our leading strand. Leading strand, life is beautiful. You have DNA polymerase, which adds the nucleotide bases on, okay? But now DNA polymerase is kind of a prima donna, and it will only add bases to the 3' end. Now, if you look, remember, DNA is anti-parallel. So here's your 3' end of the original. And this is the new one being synthesized. The light blue is the new. Here's your 5' end. So that means that where it's adding this side of this DNA strand, where you see the arrow, is the 3' end, right? Well, that's perfect for DNA polymerase. It can add bases to the 3' end. So life is fabulous with the leading strand. But then we have the lagging strand. Now remember, DNA has to be anti-parallel. So here, the darker blue is your original strand. It's the 5'. We have to have the 3' next to the 5' in order for DNA to get along, right? You've got to have a 3' and a 5' and facing each other. So now we've got an issue, because where would we be adding if we were using this as the replication fork opens? We are adding to the 5' end of the new DNA strand, this light blue. Well, DNA polymerase doesn't like that. So we had to, or nature had to come up with a way to make this work. So this is a little confusing, but the lagging strand ends up getting done in segments. And what happens is we do it in, if this is the replication fork opening this way, we're doing it in the opposite direction of the replication fork, and then we glue these segments together. And again, this is best seen. There's several videos you can watch. So here's our lagging strand. We have to add to this end. And it's really cool in the videos they show, they kind of string it out and get extra, and they do these segments, and then these segments get glued together by ligase. Now these fragments are called Okazaki fragments, okay? Now I'm gonna get into more details about this, but this was a lot to handle. So let's go ahead and look at the details. So we would say the overall direction of replication is going this way, right? However, this lagging strand has to go in the opposite direction so that it can add to its 3' end, so that polymerase. All right, so let's look at these steps. I'm gonna go ahead and pause the video, and we're gonna look at these steps in detail.